Hi everyone and welcome back to PrepFusion and welcome back to this lecture 27 of electrical machines subject. So today we will discuss about construction of DC machine. Also we will discuss about few points that why magnetic field is used as a coupling medium for DC machine, right? So basically, right, whenever we are providing some mechanical for in case of generator, we are rotating the shaft, the prime mover of the rotor of the armature. So we are providing some mechanical power as input, correct? And what is the output that we are getting? We are getting the electrical power as the output. But in between there is bit of energy conversion. What is the energy conversion? It is the conversion from the mechanical to magnetic energy, because energy is getting transformed in the form of flux, right? Then that magnetic energy in turn is getting converted into electrical energy. Okay, so in between there is a conversion from mechanical to magnetic, then from magnetic to electrical energy. Okay, just the opposite for motor. In case of motor, what we are doing, we are giving some electrical as input to the motor, and at the output I am getting some mechanical output, right? As some work done, right? The motor is rotating, it is doing some work. So in case of motor, we are giving the, what do you call, we are giving the we're giving the electrical energy as input, and at the output I'm getting the mechanical power, right? So in between there is another energy conversion medium. Energy conversion is happening in between. So first electrical energy is getting converted into magnetic energy, then that magnetic energy in turn is getting converted into electrical energy, because we have already discussed, right, the magnetic fields both interact with each other to produce the torque. It is not that directly electrical fields will interact. No, the electrical energy is converted into magnetic energy, which is used to create the magnetic field. Those magnetic fields interact with each other to create the torque, correct? So that is why we will discuss why we are using magnetic field, why we are not using electric field as a coupling medium. We can also use electrostatic energy. So mainly we use the magnetic energy, right? Magnetic energy. Okay, we are not using the electrostatic energy. Magnetic energy, we are not using the electrostatic energy. Why we are not using the electrostatic energy, we will discuss about that. Okay, then we will discuss briefly about reluctance torque, although this will not be used in case of DC machines, but this idea will be used in synchronous machines. So let's discuss about this, whatever I was discussing, right? Electromechanical energy conversion. So in case of a generator, I give the mechanical power as input, then there are few losses. So whenever I give the mechanical power as input, there is a rotor, right? This is the armature, there is a rotor. And whenever I will try to rotate this armature, there will be some what? Friction in the windings, not in the windings, friction in the bearings. So whenever you try to rotate something, there is some friction, right? Due to the friction, energy is lost. Basic thing, this we know from childhood, correct? So if I am trying to rotate this thing, there will be frictions. So bit of energy will be lost in that friction. So that energy will not be utilized to generate for electrical power generation, right? That will be lost in the friction. So the first loss that we get is the friction and the windage loss. So whenever I am rotating something in the air, right? So air also has some drag, air also has some friction. So those kind of losses are there, right? If it was vacuum, then there would have been no losses. But if as it is air and I am trying to move or rotate this pen, right? So air is actually giving it some force back. It is giving it some force drag, correct? So bit of energy will be lost to overcome that. So that energy is known as that. Those losses are known as friction and windage loss. Then there is no load coil loss. Again, same as for in case of transformers, we have seen whenever there is magnetic field, there will be no load coil loss. Both are eddy current loss and the hysteresis loss, right? But here it will be much less low. Okay, this will be much lower, much low, right? Much lower than the transformer, because transformer purely operates on magnetic phenomena. But here our other ratings are so high that this loss is very small compared to the other things, right? And then we have stray losses, as we have discussed in transformer as well. What is stray loss? So I hope you understand what is stray loss, right? It is just because the magnetic field will get effect due to the there will be the core part, there will be yoke part. The magnetic field will interact with all of the other components of the machines, and due to that bit of eddy current might flow, and due to that there might be losses. So stray losses we have already discussed. So all these losses are also known as the no load rotational loss. So whenever there is no load at all, if the load current is zero at all, these losses will happen no matter what, even if load is connected, even if load is not connected. So that's why these are called no load rotational loss or rotational loss simply. Now after all these losses are taken out, then whatever energy or power is left, that is used for the conversion. So that is the magnetic energy that I have, that will be used to develop electromagnetic power, right? It's known as the electromagnetic power, that is Eg into Ia, that we have been discussing till now, because we were actually ignoring these losses. These losses are very low, and these are like some fixed losses, right? These are not load varying losses, these are fixed losses. So we were ignoring it, but actually there will be a bit of losses due to that, and after that finally this will be EGIA. So directly I cannot use this formula that omega into T is equals to Eg into Ia. No, it is not correct actually, because there are losses here. Why? Because there are losses here in between, right? So whole of this mechanical power cannot be utilized for electromagnetic power developed, right? Whole of this mechanical power. So bit of it will be lost here. Okay. After that, whatever is remaining, that is Eg into Ia. And after this, right? Again, this we already know. This we have discussed, right? So there will be a bit of copper loss. So there are two kinds of copper loss, because the armature will have its own resistance. So there will be copper loss in the armature. So armature copper loss. Then there is copper loss in the field winding. So there is field copper loss, right? Two types of copper loss are there: armature copper loss and field copper loss. Okay, armature copper loss and field copper loss. Okay, then there is brush drop. So basically, I will discuss what is brush. Brush is the position where the current is taken out from the armature, right? So due to some friction and something, there will be a bit of drop in the brush. We will discuss about that. So this is a very low amount of loss, and this is almost constant. Although it depends on the load current, but it is like a voltage is dropped in the brush. So that is known as the VB, brush voltage drop, and it is almost constant always. So this one is the most important portion of losses in case of a generator, right? In case of a DC machine. Okay, same, just the opposite in case of a motor. So what will be the power flow in case of a motor? So power flow in case of a motor, here I will have the output power. Okay, this will be the output power, input power. Basically now I will give the electrical input power, and first of all, what losses I will encounter? Just the opposite, right? Now I will encounter the copper losses first, brush drop losses. These will be encountered first. Then whatever energy is left, that will be used for electromagnetic power development, that is for the rotation. This is equals to EB into IA. Here again, my Vs into Is will not be directly equals to EB into IA. This we already knew, because bit of losses was there. This we were actually considering while we were doing the calculations previously. So this was EB into IA. Okay. Then after this, again, as the motor is trying to rotate, there will be some friction windage loss. There will be some core loss, of course. Magnetic field is there, core loss, then steel losses are there. After all this, after removing all these losses, then finally whatever output I get is the known as the shaft power or the mechanical power output. Okay, so this is the basic flow of like power, right? So an electromechanical energy conversion device is like my DC machine is a electromechanical conversion device. What do I mean by electromechanical? So we convert electrical energy to mechanical or mechanical energy to electrical, both ways, right? So now between electrical and mechanical forms, depending on the, so is any system that transforms energy between electrical and mechanical forms. Depending on the motion and the power output, these devices can be categorized as small motion, force, torque producing devices, continuous motion machines. Okay, so these three are the basically categories of machines. Okay, so mainly motors and generators we will discuss. So what is the role of the coupling medium? As I discussed, energy transformation. So electrical energy cannot be directly transformed into mechanical energy, so there has to be a medium between it. Just like I cannot directly upload this video to you, right? What is the medium? Medium is YouTube, right? So through YouTube I upload, and through YouTube you are able to watch it. So there is a intermediate medium, right? Like YouTube is a intermediate medium. Same, this coupling medium is also there. So I cannot directly convert electrical energy to mechanical energy. There has to be a intermediary medium. So in this case, the intermediate medium is the magnetic field, right? So energy transformation occurs through intermediate coupling medium, typically magnetic field. This medium plays dual role, reacts with electrical domain. So this can talk with both, right? It can talk with electrical domain and it can talk with the mechanical domain. Like let's say you have a translator, like you don't know how to speak French, and you have a French friend, right? You have a French friend, so you will ask someone to translate. So there will be a translator person, you will be speaking in English and the translator will convert that English into French. So your French friend can understand what you are speaking, correct? And vice versa. Your French friend will talk in French and the translator will convert the French into English. So there has to be medium. So same thing is here, right? So the magnetic medium talks with both electrical domain and the mechanical domain to produce torque and to produce EMF. Okay. Now why magnetic field is preferred? Because there is another kind of energy known as the electrostatic energy. Electrostatic energy. Why do we not use electrostatic energy? Now there are few fundamental properties of magnetic field. So magnetic field fundamentally has higher energy density. What do I mean by higher energy density? Higher energy. What is energy density? Energy density is energy per unit volume. Energy per unit volume. So that is what my energy density is. Okay, that is what my energy density is. It is energy per unit volume. So if I say that inherently that is the property of magnetic field, that it has higher energy density, that means this ratio is high. That means let's say the energy density, let's say I want to develop 10 joules of energy, right? So if the energy density is higher, I will require less amount of volume to create same amount of energy. As the energy density is higher, I will not require much amount of volume. Just like this, right? Here I have a ratio x by y. So if this x by y is very high, either x can be very high or y can be low, two things, right? But if I keep the x constant, that is energy is constant, for the same energy, the volume required will be lower. So the volume of the machine, right? Machine will be go down. So machine will be of compact design, which will obviously save us in cost, right? I don't need much material, I need smaller material. So cost, it will be less costly. Okay, efficient flux linkage. Coils can store and transfer energy efficiently via inductance. So inductors are there, coils, those are known as inductors. We can easily store and transfer energy efficiently via the inductance. Okay. Now lower insulation requirements compared to high voltage electric field. We don't need like in case of electrostatic energy, right? Electrostatic energy is half magnitude of E square into epsilon, right? This energy density. This is the energy density basically. This you will learn in EMFT. So for me to have higher energy, right, the electric field intensity must be higher. If the electric field intensity is higher, the voltage must be higher. So basically more insulation protection I need to provide. But in case of magnetic field, it is mostly dependent on current. It is not voltage dependent. So I don't need higher insulation, I need lower insulation requirement. So these are few advantages compared to electric field energy, right? So that's why we generally use the magnetic field as a energy conversion device. So as I was discussing that these are the few properties of motor and generator. Motor converts electrical energy into mechanical, generator converts mechanical energy into electrical. In any system you take, in transformers as well, input energy will be equals to output energy plus stored energy plus losses, right? Whatever I am giving in to the system, some of it will be lost in losses, some of it will be stored in the system as the form of stored energy, and the rest of it will be given out to the output. So for a generator, I move my shaft, okay, and moving the shaft induces a voltage Eg, and that Eg is ultimately transferred to the load. In between there are few resistance losses, copper losses, like the field copper loss and the armature copper loss, correct? And obviously load power is not the same as the developed power because there are losses in between. Okay, that's why this is written. So there are two types of stored energy. One is the magnetic energy that can be stored in the air gap as in the form of magnetic energy. Another one is the mechanical energy. So what is the mechanical energy? So let's say this pen is there, right? If I just keep this pen in the bottom and just somehow rotate it, this pen will have some, if I just keep it in the, you try it out yourself, you just keep your pen in the table or something and try to rotate once, you will see it will keep on rotating for 1-2 seconds more. Even though you are not giving any torque, still it will keep on rotating for 1-2 seconds, then it will stop. So bit of mechanical energy is stored in the pen, due to which it is continuing its rotation, after which all of the energy which was stored, that is getting lost due to the friction in the table, right? So that those kind of energy is known as mechanical energy. So initially if I just give some torque in the prime mover. Due to inertia, it will rotate for few more seconds or whatever time interval. After that, finally it will stop due to the friction in the air, right? So that is what is known as the mechanical energy of the moving parts. So yeah, that is what we have discussed basically. So mainly what kind of energy losses are there? So energy losses we have already discussed, that mainly there are this no load losses, okay, that is due to the rotation losses, and we have the copper losses and the brush drop loss. So mainly these are the three losses. So in case of a DC machine, what are the main three losses? One is the no load, rotational loss, another one is the copper losses, okay, both in the field windings, in the field winding and in the armature, field and armature. And the third one is what? Third one is the brush drop loss, which is negligible actually, very less low. Brush drop means there will be a bit of voltage drop in the brushes, 1 2 volts, very less amount of drop, right? Brush drop loss, okay. So these are the losses that will happen. Now one more thing you have to keep in mind is, in case of a motor, right? Remember that I told you that the motor's developed torque, if the motor's developed torque is in the clockwise direction, then the load torque will be in the opposite direction for it to rotate with a constant speed, right? This we have discussed in the previous lecture. So always remember, whatever is a developed torque, the load torque will be in the opposite direction. Same case of generator. So if I rotate the prime mover in the clockwise direction, this is my torque, input torque direction, right? That I am providing. Now the developed, due to some this induced voltage will be developed. And what do I understand by Lenz's law? Lenz's law states that the induced voltage will be in such a direction that it will oppose its initial cause. So how did this voltage got induced? Because I was rotating this armature, right? If you remember, this voltage got induced because I was rotating the armature, right? First lecture, correct? So hence it will induce a voltage such that it will oppose its initial cause. So the developed torque in the machine will be in the opposite direction. So in this example, as the input torque is in the clockwise, developed torque will be in the anti-clockwise. If let's say, if the input torque was in the anti-clockwise direction, then the developed torque would have been in the clockwise direction. So this basically, the always remember that the developed torque and the load torque both will always oppose each other. So developed torque and the torque of the load or the input torque will always oppose each other, right? So I will write key point, developed torque and load slash input torque will always oppose each other. Okay. So yeah, that is the thing over here. I hope you have understood this basic point. So these are the few key points that I wanted to tell to you guys, right? Okay. So same thing here as well, that here, right, in case of motor, what will happen? In case of motor, I will provide some supply and this voltage will be induced in such a manner that it will oppose its initial supply. So basically it will try to oppose. So that's why this also will be plus sign, same as transformer, right? If this is plus, this also will be plus, right? Because it will oppose its initial cause. So initially what was happening, if let's say this back EMF was not there, so what was the current? Current was simply, if I neglect the motor resistance, it was Vs by R, huge amount of current was flowing in. So it does not like sudden change in current, right? So it will oppose. So it will produce EMF EB such that this IS current is reduced. So that's why my IS current in this case, in case of a motor, is Vs minus EB by R, right? And in this case, what is the current I? So in this case, the current I, right, it is like as I'm generating now, so Eg, it will be Eg minus V divided by R. Okay, these are the basic relations, this we already know. So just wanted to give you an overview about the energy transfer and about the losses. Now let's discuss about the, so this is the energy flow, basically electrical input for motor. Electrical input will be there, magnetic field will be built, then back EMF will be developed. Okay, and that back EMF, due to the back EMF and the magnetic field interaction, due to the current and the magnetic field interaction, torque will be generated and ultimately the machine will rotate. Okay, this is the general flow, correct? And for generator, I will drive the prime mover, which will provide a relative motion between the magnetic fields. Due to that, a voltage will get induced, and due to that, it will drive a current to the load. Okay, generator absorbs mechanical energy because I am providing the mechanical energy and delivers electrical energy. Motor absorbs electrical energy because I am providing the electrical energy and delivers mechanical energy in the form of rotation. Okay, so this is about the energy flow. Now let us discuss about singly and doubly excited machines. What do I mean by singly and doubly excited machines? So singly excited means, as the name suggests, that there will be only a single coil that will be excited. Only one of the stator or rotor will be excited. Generally you see transformer. So transformer, only a single stator is there and primary winding is excited, right? And in induction motion as well, only a single winding will be excited, right? Energy will be transferred via induction. In transformer as well, energy is transferred via induction, magnetic induction, and in induction motor as well, same thing will happen. Now what is doubly excited? In doubly excited, both the stator and rotor will be excited. Both the stator and rotor will receive independent excitation. In case of DC machine, we have already seen there is a field winding, there is armature winding. Both of them carry independent current and both of them are excited differently, right? And synchronous machine will also be a doubly excited machine. Self-excited machine, already we have discussed that excitation comes from the same source, like shunt and series machine. Separately excited, separate sources are there to excite the field winding. So we already know why we need a doubly excited machine, because we need the interaction between the current of one of the windings and the field of the other winding. Then only torque will be produced. In case of DC machine, in induction machine, a different principle will be used, that is a magnetic induction. Okay, one more property is that in case of DC machine, right, the poles will always alternate. Okay, poles of stator or rotor always will alternate. So if I have north pole here, I cannot have south pole here. In case of interpoles, I can have in north pole here, but that is interpole, that is not actual pole, right? That is not actual pole. So this is not possible, not possible, not possible. Okay, only possible for what do you call, interpole, not possible. Only possible if it is an interpole, it is not an actual. What is interpole? We will discuss about that. We will discuss about interpole later on. Okay, so these kind of like poles are not possible. So this is just like what it is, it will just behave like a one single north pole. This overall combination will just behave like a one single north pole, and this overall combination will behave like a one single south pole. So it will not be a 4-pole machine, it will be a 2-pole machine. So this equivalently I can write it will be a 2-pole machine. This will behave, I will write here, will behave as two-pole machine. Okay, this will behave as 2-pole machine. Okay, and so how will I, what will be the resultant north pole then? So if I copy this, right, the resultant north pole will lie somewhere here, like this whole thing will be the north pole and this whole thing will be the south pole. So I can directly write, so this will be somewhat here. This whole thing will behave as a single pole only. So yeah, this will be the pole basically. Okay, sorry, this whole thing will behave as a north pole, and this whole thing will behave as a south pole. Okay, so although the diagram is not that great, but yeah, that is what will happen. So the field interaction will be like this, right? So the field lines will go like this. Okay, but here this actually the it will behave here, the number of poles will be 2, but this will behave as a 2 pole machine. So even though this will behave as a 4 pole machine, even though here, right, I have 4 poles, but ultimately it is behaving as a 2 pole machine only. So the poles must be alternating, otherwise it will not behave as a uh, it will not behave as a 2 pole machine. Now how can you make this uh, poles direction same, right, same or different? How can you change it? So what you can do is that all depends on the winding orientation, right? All of it depends on the winding orientation. So if I like do one thing here, this is not working, something, okay, I just want to, yeah. So you must look at the current direction. You must look at the current direction. So how do I make this north pole and north pole, and how do I make this north pole and south pole? So it all depends on the current direction. So how the winding is oriented. So here I have the windings, right? So let's say if this was cross, just hold on, if this was cross and this is dot, right, this is cross and this is dot, so direction is something like this. The field lines will come out of the north pole. So for me to make a north pole, the field lines always should come out, right? Field lines always should come out. Same thing here, right? If I want to make a north pole, the field lines should come out of the north pole. So again, look at your fingers, it should come out, it should go downwards, right? So if it is going downwards, that means what? This, right, this will be the cross and this will be the dot, because that is what my right hand says. If I curl my right hands along the direction of the current, it is like this, right? So this is the field direction. So that's why the overall this one behaves as the north pole, and this, how it will behave as a south pole. For a south pole, the field should come inside the south pole, the flux should come inside the south pole. So this is the direction of the field, right? So in the bottom it should go in the top it should come out. So in the bottom it should go in, it should come out. So please keep in mind, please do see the current directions very well. Please do see the current directions very well. Okay, so same here as well. Again, south pole, the field should come inside the south pole. So it should come inside the south pole. So it will be incoming in the left hand side and coming out of the screen on the right hand side, right? So always look at the current direction. If you want to identify whether it is a north pole or south pole, always look at the current direction. Okay, so yeah, that was it basically. Here as well, again, what will be the current direction? Here, if this is a north pole, then it will just follow this direction, right? Cross dot. So this will be cross dot. So I'll just hold on, I will just, okay, so it, for a north pole, it must come out of the pole, right? The flux must come out of the pole. So this will be cross, this will be dot. So if I rotate my fingers, this is cross, the bottom one is cross, that is going into the screen, and the top one is coming out of the screen. So here, right, it must go into the pole. It must go into the pole. So if it goes into the pole, that means the right hand side will be a cross and the left hand side will be a dot. So this will be cross. So this is not proper, right? This is cross, this is dot. Here again, it is coming out of the north pole. So the top one will be a cross and the bottom will be a dot. Okay, here again I see it should go into the south pole, so this will be a cross, this will be a dot. Okay, so that's how you can identify that whether it is a 2 pole or 4 pole, even though here physically there are 4 poles, but it is will behave as a 2 pole machine only. Physically there are physically there are physically there are 4 poles, right, but it will behave as a 2 pole machine. So that is the disadvantage if poles don't alternate. If poles don't alternate, it will behave as a 2 pole machine or a lower pole order machine. So that this is also a very important point to understand. So let's discuss about a case why the poles of the stator and the rotor must be same. Okay, let's discuss about this very like basic property. If let's take example, if let's say the rotor has 4 poles and the stator has 2 poles, then will any torque be developed? That is what we are trying to discuss here. So let me write down the poles here, right? So let me write, this is, let's say this is N2, this is S2, this is N1, and this is S1. Okay, so these are the pole locations basically. So now if I try to develop a torque, how will a torque be developed? So the magnetic field lines will be like this, and the field lines of the armature, right, will be like this, will go from N2 to S2, correct? This field line will go from N2 to S2, and the same field line, so this will go from N2 to S2, and this will go from N1 to S1, right, correct? So and magnetic field lines will pass like this, north to south. So one key point to note here is that this and this are parallel lines. These are parallel lines because like it's just a 4 pole machine, that's the property. This will be parallel. So how a force is getting developed? We know the force is developed by the angle between the stator field lines and the rotor field lines, correct? So let's assume this as delta, right? If this is delta angle, so if this is delta angle, as these are parallel with each other, this also will be delta, right? Now in which direction this will develop a force? I want to know in which direction this will develop a force. So here basically this N1 will get attracted to the south pole, right? This N1 will get attracted to the south pole, correct? So it will get a force of attraction in this direction. This will be the direction of force of attraction for N1. And same thing will happen, basically this N1 will get repelled by this north pole, and same will happen here, that this N2 will get a force of attraction here and it will receive a force of repulsion from N, right, north pole, force of repulsion. So what will happen is that I know the MMF is same, right? MMF and whatever currents they are carrying is same, right? So these angles are same. So this force of attraction and force of repulsion both will be basically equal. So there is no net torque getting developed. So I have just compared this attraction with the south pole for N1 and repulsion with this north pole for N2. Same thing you can do for attraction with the south pole for N2. So a force of attraction will be there and a force of repulsion will be there from this north to N1, right? So again you will observe that there is no net torque developed because both of them are equal in magnitude and in opposite direction. So here there is no net torque getting developed. So in this case, if the rotor and stator poles are different in number, there will be no net torque developed. Okay. Now let's discuss about this, right? If the number of rotor and the stator poles are equal, then will there be any torque? So in this case there will be torque. Okay, we will exactly discuss about that. So let's now move on to the second case. So if both the number of rotor and the stator poles are equal, then again I can, like, now I have taken a 4-pole machine. So if I have taken a 4-pole machine, what will happen? So again, okay, this is wrong, right? This should not be north and north pole. This should be north and south pole. Sorry for that. So basically, this will be south pole. This will be north pole here. Yeah, now it is fine. Okay. So now if I want to calculate, if I place the same N1 N2 everywhere, right? The locations are same, they are not changing. So let's say this is N1, this is the S1 south pole. Basically, previously what were the locations? Locations were, yeah, okay, sorry, this is N1, this was previously N1. This is N1, right, somewhere here, and this was S1 somewhere here, right? Sorry, this was S1 somewhere here, this was N2 somewhere here, and this was S1 somewhere here, S2 somewhere here, right? So now there are many kinds of forces, right? So if I see this north pole will get a force of repulsion from this N2, and it will get a force of attraction from the south pole, right? So overall the force direction will be somewhat like this, okay, for these two poles, right? Now for this N1 again, if I see, it will feel a repulsion here, and it will feel a attraction of this S pole, okay. So I have considered the force due to this and this pole in the N1 and N2. So I see there is a clockwise movement. Same thing you can apply, same thing again you can apply this N2 with respect to these two poles and this N1 with respect to these two poles, okay. I will apply the same thing. So this N1 will feel a force of repulsion due to this north pole, correct, but this is very far away, right? So the effect will be very low. The effect of this N2 and N will be very low because distance is higher. Distance increases, the field density will reduce, and of course the force also will get reduced. So I am just taking into effect whichever poles are nearer, right? So for the south pole, these two poles are nearer. So this south pole will feel a force of attraction due to this north pole and will feel a force of repulsion due to this south pole, right? So the direction of rotation will be somewhat like this. And here again for the south pole, which is nearer, these two poles are nearer, right? So again it will feel a force of attraction due to the north pole, and it will feel a force of repulsion due to the south pole. So I have just used repulsion and attraction principle to derive that yes, there is a net torque developed. There is net torque developed. Now again it depends on the current direction, okay, but there will be some net torque developed. Whether it will be in the clockwise or anti-clockwise, it all depends in the current direction, but there will be a net torque developed in the machine, okay. That is the important point that you must note, okay. In this case again the same principle if I apply, only there are one pole, right, and this N2 is nearer to this and this N1 is nearer to this. So I was just taking into effect of this pole for this N1 and of this pole for N2, right, as it is more nearer to this than this, right. If it is in the middle, anyways both forces will cancel out. Whichever one is nearer, I will take that effect, okay. So yeah, I hope you have understood this basic point. So the number of rotor and stator poles must be equal for torque to get developed. Now let's discuss about constructions. So what are the parts of a DC machine? Briefly we have discussed in the first lecture. So again I will go through this. So mainly a DC machine will have a stator where the field windings will be placed, while the field will be generated, rotor where the rotating part will be there, and the armature winding will be connected. And for an induction machine it is known as the squirrel cage, okay. Induction machine it is known as the squirrel cage. Then there will be air gap, so space between the stator and the rotor, essential for smooth rotation and magnetic coupling, okay. So air gap is basically, I am rotating the machine, right, I cannot just place the two things very close to each other. As it is moving, it can actually damage the other part, right. So I cannot place them too close, I have to provide some sort of air gap. Although air gap is unwanted because it will increase the reluctance, right, reluctance will increase, but we cannot avoid it, right. For proper safety measures we cannot avoid this. So for proper safety we have to somehow like keep this no matter what, right. That is the important portion. Now let's discuss about salient pole synchronous. Okay, so now how much air gap is there depending on the machine, right. So in case of a synchronous machine, salient pole synchronous machine, the air gap is the highest. Then we have DC machine which has the next highest air gap. Then non-salient synchronous machine, don't worry, we will learn this, we'll learn this, what are these. Then slip ring induction machine. Why the air gap here is lower? Because here the energy transfer is going from magnetic induction, right? And basically if I give too much of air gap, then proper alignment and proper energy transfer won't happen, right? Then we have squirrel cage induction machine. So we will discuss about this. So just wanted to give you a comparison, like how the air gap is in different places. So this is the construction basically. So here this is the rotor, and in the rotor these are the slots. Basically in these slots there are conductors placed, right? So this is known as a spider. So that is in the middle portion, that is known as a spider, and these are the field windings, and these are the poles. Basically if you see, this is the field pole, and these are known as also teeth. Okay, and this is known as the pole shoe, because this is the ending of the pole, and this is known as the base at which the machine will be placed, and yoke is the overall outside body of the machine. So these are few construction, and again armature core will be laminated. Why? Due to eddy currents. Due to eddy currents, the armature core will be laminated because flux is interacting there. So these are few constructions there. So yoke is there. Yoke is the outer frame of the machine, and it provides mechanical support and magnetic path for the flux to flow, right? So generally for small machines cast iron is used. For large machine, cast irons and rolled steel are used. Okay, I hope you have understood this very basic point. Okay, then I have this field system. So what is the field system? So field system again has many components, mainly 3 components. So one is the field poles. So this, right, these are known as the poles. This whole thing is known as the pole basically, in which the winding are placed. So made of laminated cast iron, or laminations are used to minimize, again as the windings are there, right? So field lines pass through, so we have to make laminations. So these are the basically the laminated laminations. So it is used to minimize the eddy current, and each pole carries field coil. So each pole will carry field coil, as it is shown here. Right? Here I can show you that these are carrying the field windings, and field coils are the ones that actually carry the excitation current, right? So wound around the pole cores, and it is enameled copper wire. When DC current passes through it, it magnetizes the pole to produce a required magnetic field. Okay, now at the end we have pole shoes. Pole shoes are these endings, right? These are known as the pole shoes. These widened extensions at the end of pole cores. These are the widened extensions at the end of the pole cores. So why are these actually extended? Why are these extended? Previously also I have discussed this, right? Because previously my flux was purely sinusoidal. If this was just a simple pole, right, here the air gap was least, then the air gap was increasing. But if I extend this, right, what is happening? The air gap is constant, right? This we had discussed previously as well, that the air gap here is constant, G, G, G. Okay, so this is constant. So if air gap is constant, mmf is same, reluctance is same, so the flux also will be same. So that's why we want to make our magnetic field flat topped. That's why we make it like this. It is also known as arc shaped. So it ensures constant air gap to get a uniform flux density. Okay, used in DC machines to minimize the ripples, right? Because we want to enhance the average voltage, we want to reduce the pulsations in the rectified voltage. Okay, now there is another kind of pole known as chamfered poles. So what are chamfered poles? Chamfered poles are just the opposite. If I want my flux to be purely sinusoidal, then I will use chamfered poles. What does it mean? It basically means the air gap increases at the pole edges. So the air gap will be lowest in the middle of the pole, and the edge it will be highest. So air gap will increase, right? Here air gap will increase, and it will be lowest in the middle. Lowest, the air gap will be least, and in the edges the air gap will be the highest. Okay, so this actually is used to reduce the armature reaction. Okay, this is not used to shape the waveform, because we want this flat top waveform only, but there is a phenomenon which we will discuss in the next lectures, known as armature reaction. So to reduce that, sometimes we will use chamfered poles. Okay, so yeah, that was about the poles, like chamfered and the this pole arc, right, arc shaped pole. Now let's discuss about axis in electrical machines. Okay, there are two kinds of axis in electrical machines. In the analysis of rotating machines like DC machines, synchronous machines, we commonly define two key reference axes based on the magnetic field orientation and the machine geometry. Okay, so there are two axes. One is known as the direct axis, another one is known as the quadrature axis. So what is direct axis? So direct axis, also known as the polar or magnetic axis. Direct axis is aligned with the center of the magnetic pole, that is along the axis and the maximum magnetic flux density produced by the field winding. So direct axis is the direction along the magnetic field lines. Okay, it will be in the same direction along the magnetic field lines. So if I have a north pole here, south pole here, so this will be the D axis basically. Now what is the key? Q, quadrature. Quadrature means 90-degree phase shifted. So what is the Q axis? Q axis, also known as the neutral axis, interpolar axis, or the perpendicular magnetic axis. So Q axis is electrically 90-degree apart from the direct axis. It lies between two adjacent field poles. So if these two field poles are there, so direct axis will be along this direction of the field, and Q axis will be 90-degree here, right? Here. Where the magnetic field will be lowest, because magnetic field will be passing like this only, right? So here the magnetic field will be highest, here the magnetic field will be lowest. So Q axis will be along that direction in which the magnetic field is lowest, or it is quadrature to the direct axis. Okay, so you can read through things. So just wanted to define what. So in this case, the direction of the, if the direction of the field produced, magnetic field produced is in this direction, then the quadrature axis will be 90-degree phase shifted, right? From this physically 90-degree phase shifted. So these are the Q axis and the direct axis definition. That's it, very basic thing. So physically in the Q axis, the carbon brushes are placed because there will not be any short circuit. Don't worry, we will understand all this when we will learn about commutation. Just understand what is direct axis and what is Q axis. That's it. Okay, these are the important points. So these are the comparison basically. So direct axis is the position where the flux will be maximum. It is along the direction in which the flux is maximum. Q axis is along the direction in which the flux is minimum, ideally 0. Okay, it is along the center of the pole. So direct axis is along the center of the pole, and Q axis is basically between two poles. So here I have north pole, here I have south pole. So between the two poles, here the Q axis will lie. Okay, and yeah, these are the direct axis and the Q axis. So in this 4-pole machine, can you identify what is the direct axis and the Q axis? In the 4-pole machine, this right, this is the basically direction. So this will be the D axis. This will be the along the field lines. This will be the D axis. Here as well, this will be the D axis. Let me pick a different color. Let me pick a dark color. So here, this will be the D axis. Again, this will be the D axis. Correct? North to south, north to south. Again here, this will be the D axis. This will be the D axis. What is the quadrature axis? Quadrature axis will be this. This will be the quadrature axis. Let me choose a different color. This will be the quadrature axis. This will be the Q 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 axis. So individually, the locations of the direct axis and the Q axis, I hope you have understood, right? Okay. So let's now do few questions, whatever concepts we have learned till now. So in a DC machine, the pole shoes primarily serve which purpose? What is the pole shoe serve? Reduce the reluctance of the magnetic path, distribute the flux to obtain uniform flux density, provide support for the field windings, perform all of the above functions. So pole shoes actually will provide everything, right? So if the field windings are placed there, if I place the field windings without the pole shoes, what will happen? The field windings will just drop down. They are used to provide support as well, right? So what do I mean by it? So what do I mean? So this, right? This is the phone, right? If I just keep this phone without this, it will just drop down. Same for windings. So if I have this pole like this, right? And if I just wound my windings here, and I don't have any support here, right? So what will happen? This windings will simply drop down. If the support is there, this windings, this pole shoe can provide a support for the windings. So yes, it does provide support for the windings. This is correct. It is used to distribute the flux uniformly for arc-shaped poles, right? Also, it is used to reduce the reluctance by reducing the air gap. So it performs all of the above functions. So option D will be correct. Okay. Let's read the next one. In a DC machine, the air gap near the pole tips is made larger than the center of the pole primarily to reduce armature reaction effects. Don't worry, we will understand. It is known as the chamfered folds. We will understand this more. We'll go more depth once we will understand what is armature reaction. Okay, don't worry. Just understand that we make this chamfered poles to reduce armature reaction, right? In DC machine, the spatial distribution of air gap flux under no load condition is what? In DC machine, the spatial distribution of air flux under no load condition. So in DC machine, right, it is flat top. So by default, we try to make it flat top because the poles are not chamfered, they are what? Pole arc shape, right? So by default, the air gap flux distribution of a DC machine, it is flat top. It is not proper pure DC, right? It is not pure sinusoidal as well, because I've told you why it is not pure sinusoidal. We make it flat top because we want to reduce the what do you call the AC component. We want to reduce the AC component. Basically, we want to reduce the ripples. So this we make it flat top to reduce ripples. This we have already discussed previously as well, and today also we have discussed already. Correct. So now let's come to the third part of the machine, that is the armature rotor. So armature rotor already have given you a bit of hint that it will be laminated. So if you see, these are all laminated, right? It is all laminated. These are known as slots in which the windings will be placed. In these slots, the windings will be placed, and lamination is done to reduce the AC current. Sorry, is to reduce the eddy current, and this is known as the length. It is cylindrical in shape. So armature is the rotating part and is mounted on the shaft. Okay, constructed from laminated steel sheets stacked together to form a cylindrical core. The laminations are insulated from each other to prevent eddy current. This we already know. The periphery is slotted according to accommodate armature windings. So the slots are used. These are the slots that are used to accommodate armature windings. Okay, so this is armature core. Now we will discuss about armature windings. Okay, so armature windings are the windings that are placed inside the slots of the laminated armature core. They are made from copper conductors, often with insulations, because we don't want them to short circuit. We don't want the conductors to short circuit each other, right? So these conductors cut the magnetic flux, due to which the EMF is generated, or due to which the force is generated, right? So for generator, EMF is generated. For motor, force is generated. Okay, so this is the task of a armature winding. Then we have commutator. So I have told you what is the commutator. Commutator is the part that is responsible for converting that AC induced EMF on the armature winding to DC. So the commutator, also I have proved how we convert, right? I have proved in the first lecture of DC machine. So a commutator is a mechanical rectifier that converts the generated AC within the armature winding into unidirectional DC output in generators, or ensures unidirectional torque in motors. So for a generator, it ensures a unidirectional DC output, or for motor, a unidirectional torque. If let's say the commutator was not present in the motor, what will happen? Basically, if commutator is absent, for generator it is very easy to understand that it will generate a DC output, DC EMF voltage, right? For motor, what will happen? For motor, right, the torque will then, if the commutator is not present, in motor, then the torque, average torque, right, then the torque will be pulsating. Actually, torque will be not be pulsating, torque will be AC, and if the torque is AC, right, alternating, then the average torque will be 0. Torque will be 0. So machine will not rotate simply, right? Because like at a certain stage it will like experience a torque in the right hand side in the clockwise direction. Again, in a certain stage it will experience a torque in the anti-clockwise direction. So anti-clockwise direction in the clockwise direction. Okay, so that is a problem. Basically that is a problem. So overall average torque will be 0, because ultimately it will not neither move in the clockwise or anti-clockwise. Overall torque will be 0. So commutator, I have already proved to you how we convert, right, from AC to DC in the first lecture. So that it is also known as the mechanical rectifier, because electronic rectifier we have learned, like you will learn in power electronics when you will study the power electronics from me. So there you will see that I have a electronic rectifier where we use diodes, right, or SCRs. But here we don't have electronic component, we have everything mechanical. So this is a commutator basically. This is also another picture for a commutator. So we have a gap here, and in the gap basically the current direction changes. correct? So don't worry, I will prove it again. I will prove the commutation portion again, don't worry. I will prove the commutation again in the next few lectures, don't worry. For now, just understand the parts of a DC machine. Okay, so so as it is a mechanical part, that's why it is called as a mechanical rectifier. Rectifier because we are converting from AC to DC, mechanical because it is a mechanical part. Okay, so segments are mutually insulated by mica sheet. So these segments will be insulated here by mica sheet. So let's now discuss about the next part, that is known as the brushes. So what are brushes basically? So brushes mainly are used as an electrical contact because it is the connection between the stationary and the rotating part, right? Because commutator will rotate and brushes is the stationary part where the commutator will touch, due to which current will be passed, right? Because the other end the load is stationary, right? So it is the connection between the uh, rotating commutator and the stationary part. Okay, these are the brushes, right? Here the commutator will rotate, it will slide, it will touch the brushes through which the current will flow. Okay, that's why there is a drop in the brushes. That's why we say there is a drop in the brushes. So generally if something is rotating, right, and if two things are touching each other, so there you see the, you hear the sound, right? So there will be a bit of friction, there will be a bit of wearing and tearing. So generally we have to keep on changing the brushes of a machine, DC machine, right? Otherwise it will not work in its full potential. So that's why as there is some wearing and tearing, there is some losses, we say that there is some drop, that is known as the brush drop. Okay, generally we say that it is generally like it is a loss basically. So we say that it is generally like VB, the drop across the brush is generally 1 to 2 volts. Okay, and the loss, how much is the brush drop loss? It is VB into IA. This is the loss in the brushes, generally assumed to be almost constant if the load is not varying. Okay, so again, what is a shaft? Shaft is this one that is used as a backbone of the rotor. So this is the, like let's say this is the shaft, right? So if the rotor is there, something has to hold. So the shaft actually holds the whole cylindrical structure. So this is connected in the center. The shaft is connected in the center. That will be connected to the prime mover in the outside world. Okay, so shaft is the outside world that keeps on rotating. Okay, so it is a mechanical backbone. It supports the armature core and the commutator as well. It supports both the core. So this is the shaft is the one. Now commutator is the one that is electrically connected between the rotating part and the brushes, and the shaft is the part that is mechanically connected. So shaft is the portion where you will connect your mechanical load. Let's say you have your pump, right? You have your pump like water pump or something, mechanical load is there. So shaft is the part that you will connect to the machine, to the mechanical load, and the other portion of the shaft is there for providing support to the armature core. Okay, this was about the shaft. Now few things we will learn about armature winding, and in the next lecture we will discuss more about armature winding. So today we will discuss few things about armature winding, and in the next lecture more things we will discuss. Okay, so let's start. So armature winding is the part of an electrical machine where the actual energy conversion happens, because the current in the winding interacts with the magnetic field with the stator, due to which a force is getting generated. So armature winding is the part of an electric, so this way I have already written. It either carries the current from the source in case of motor, or delivers the current to the load. Because in case of motor we take the electrical energy and convert it into mechanical energy. In case of generator we take the mechanical energy and convert it into electrical energy. Okay, now there are two kinds of armature winding. One is closed and open winding. So in case of DC machines, the armature winding is closed. How is it closed? It is closed because it, like these are my brushes and these are my armature windings, right? Okay, so individually these are my armature coils and it follows a closed path. So if the winding follows a closed path, then it will be a closed winding. If it follows an open path, this will be open winding. This is generally used in AC machines. In synchronous and induction machines, we will see this open winding in synchronous and induction machine. For now, you just understand that your armature winding will be closed. Okay, in closed winding the current can circulate continuously through the windings and commutator, right? So here, right, the picture is there, I guess. It's not here, right? So okay, the picture is not here. Okay, I have to go back in the starting. This is 123 page. So if you see in the starting, right, we discuss about the commutation and all those things. What is, yeah, here. So here, right, it is basically closed. it is a closed loop, right? It is not open. But in case of synchronous machine, you will see that the winding will be open. Okay, let me go back to 222. So let me paste it over here if I am able to get any space, right? So I guess, yeah, these are the brushes, these are the commutators. Somehow where will I get the space? That is what I am thinking about. The open winding is here, this is the closed winding. Okay, so this is the basically closed winding, right? In DC machine it is closed winding. In case of AC or synchronous machine, it will be open winding. We will discuss about that when we will learn about synchronous machines. Okay, so this was the distinction between the open and closed winding. Now pole pitch, I have already told you that pole pitch is the angular displacement between the two consecutive poles. So it is always 180 degree elliptical. Already I have derived it, right? So pole pitch will be always 180 degree elliptical. It will always be equals to 180 degree elliptical. But mechanical, what it will be? I have already proven you that mechanically it will be equals to P by 2, right, into 180 basically. Am I correct? Sorry, not this. Sorry. Mechanically it will be, so pole pitch, right? Pole pitch mechanically what it will be? Pole pitch mechanical, it will be 2 by P into 180. Am I correct here? I think I am correct. Yes. Yeah, 2 by P into 180. It is correct only. It is basically 360 by P. So in a whole 360, how many poles are there? So let's say currently there are 4 poles, right? In a whole circle. So 360 by 4. So the pole pitch will be 90. Exactly, right? It is 90 degree displacement. Mechanical, right? Mechanically, physically, actually, the angular displacement is 90 degrees between each consecutive poles. But physically, what electrically there will always be 180 degree phase shift between two consecutive poles. Why? Because the magnetic flux is a sinusoidal. Already I have explained this in the first lecture of DC machine, so I am not explaining it over again. So very basic formula I get, that is my theta m theta e equals to P by 2 into theta m, right? A very basic formula which we had derived previously. Sorry, not this, right? Theta, sorry, am I writing it wrong? Yeah, it is correct only. It's correct only. Yeah, because it will be 180, so P by 2 is 2. Yeah, it's correct. So theta e will be equals to P by 2 into theta m, right? Electrical angle will always, how do you remember? Sometimes you tend to forget this formula. You tend to forget this formula. Either you can draw this diagram like this, you can remember. Physically you can draw the diagram, and from here you can remember what is theta e, theta m. From there you can derive the expression. Or generally you remember that theta is always will be greater than or equal to theta m, because at minimum number of poles can be 2. So if number of poles is 2, in that case theta e will be equal to theta m. In all other cases, the electrical angle will always be larger than the mechanical angle. Got it? And poles obviously will be in pairs. Okay, so this is the pole pitch basically. Now there are many terms of pole pitch, right? Many kinds of pole pitch. One is the angular pole pitch. So this one was the angular pole pitch, right? Now there are different kinds of pole pitch. That is known as the so this pole pitch is known as the angular distance between the centers of the two adjacent poles. We have already discussed about this, right? We had already discussed about this. Now there are different kinds of pole pitch as well. So another kind of pole pitch is the number of pole pitch in terms of conductor. So I have another definition for pole pitch, where pole pitch in terms of conductors. So what is that? That is basically, if let's say I have z number of conductors and I have p poles, then the pole pitch, right, in terms of conductors, if I want to define pole pitch in terms of conductors, it will be z divided by p. Okay, so yeah, let's take an example that if my z is, let's say, is 48 and if number of poles is 6, so this will be 48 divided by 6 number of poles. So pole pitch in this case will be 8 conductors per pole, right, per pole. So this is actually also another definition for pole pitch. Okay, now pole pitch in terms of slot also you can define. You can define pole pitch in terms of slot. So there are many ways how you want to define the pole pitch. So again, slots meaning the number of slots that is present here, right? So these gaps are known as the slots. So if I want to say pole pitch in terms of slots, so this is the pole pitch in terms of angle. Okay, there can be many definitions for pole pitch, right? So pole pitch in terms of slots, if I want to write, it will be what? Pole pitch in terms of slot. So yeah, let me reduce this. I'm going to reduce this and let me keep. Can I keep it over here? No, I cannot. So the pole pitch in terms of slot, it basically means the pole. If I have, let's say, S slots in a armature and P is the number of poles, then the pole pitch in terms of slots will be S upon P. Okay, this will be the pole pitch in terms of slot. So let's take example that, let's say, if the number of slots is 12 and number of poles is 6, so it will be 2 slots per pole. This will be the pole pitch. Okay, like this you can define all these things basically. Okay, all these things can be defined like this. Okay, so I hope you have understood this basic point. And yeah, another key term there is, that is the pole arc. What is the pole arc? So pole arc is the actual circumferential distance occupied by a pole, right? Because let's say this is a, like, the pole pitch is 90, so my pole should overall cover a whole 90 because I have 4 poles here. So the pole should overall cover this whole 90 degrees, right? Okay, pole should overall cover this whole 90 degrees. Okay, so sorry, let me, you get confused what is GNA. I will discuss about GNA later on. So pole should actually cover 90, but obviously it will not overall cover the 90, right? I have to provide some gaps between these two. So it is only covering this much distance, right? It is only covering this much distance. So let's say this was some angle, mechanical angle, it is covering, let's say, some alpha angle, but it should have actually covered 90-degree angle. Now this alpha angle is in mechanical, right? This alpha angle is in mechanical. So this will be what? The pole arc will be what? Alpha divide by the 90 degrees in this case, but we have to write this in radians, right? Please write this in radians, write the pole arc in radians. So this will be alpha divided by pi by 2. So this alpha also will be in radians. Okay, so what does this pole arc signify? Basically, this is my pole arc. Basically, this is my pole arc. What does this pole arc signify basically? So what is this pi by 2? Is it familiar? This pi by 2 is basically the pole pitch, right? Angular distance between the two centers. What is the pole pitch in this case? Pi by 2, right, in radians. So it is basically pole arc is equals to pole arc, not the pole arc, sorry, not this, this is not pole arc, sorry, this is the ratio of pole arc. Pole arc is what? Pole arc is the actual circumferential distance that the pole will occupy divided by the pole pitch. This ratio actually gives me a very important number. This ratio is actually 0.7 to 0.9. So this alpha by pi by 2 is basically the pole arc divided by the pole pitch. Okay, this ratio is pole arc divided by the pole pitch. Okay, so now what more can I discuss? Now why is this significant? So if this is 1, that means what? Pole arc, whatever area this pole shoe will cover, and the pole pitch are same, so there is no gap. Now if there is gap here, that means until this region, this much region, the air gap is same for the armature conductors. That means the field flux density will be constant. The flux density will be constant. So flux density is constant only for the region of the pole arc, right? And what is the pole pitch here? The pole pitch is this whole region, right? This whole region. So if we see, I am covering this whole pole. So in this whole pole, the flux density direction will not change. As soon as I move to this next pole, right? Obviously it is north pole, it is south. So the flux density direction also changes. So basically this much distance is known as the pole arc, and this whole thing, right? This whole distance is known as the pole pitch. Okay. So now I hope diagrammatically you have understood what is the difference between pole arc and pole pitch, and this much distance is actually known as the clearance, because I cannot obviously make it very close to each other. I have to provide some amount of clearance for mechanical working, right? Because parts will rotate. If there is no clearance, if something gets missed out, right, it will just crush. So this is rotating, it is rotating at a very high speed. So if I don't provide any gap here, let's say some of the rotor something comes here and it gets crushed with this, right? Like huge things will, I mean things will get damaged basically, right? So we want to provide a clearance. So this is known as the clearance, basically the gap between the pole arc and the pole pitch. It is known as the clearance. Okay, so yeah, I hope you have understood this basic point. So what is the area covered under each pole? How do I find out the area? So pole is, this is a 2D figure. So if I want to draw the 3D figure, right? If I want to draw the 3D figure, so the 3D figure of a pole will be somewhat like this. This is the 3D figure, right? So in 3D, what I can say is this is the basically the axial length, right? So what is the overall area covered? Area covered will be this, right? This pole arc into the axial length, because if I want to see it from the top, it will be basically something like this, right? Something like this, just a rectangular sheet, correct? So this is the overall area that the flux will be projected from. So what is this area? This is known as the actual area under each pole. So I will write here actual area under each pole. Okay, so what is the actual area under each pole? It is basically it will be basically so this, right, is the actual length. So this is the actual length, sorry, this is the actual length, this is the L, actual length into the this circumference. That will just give me the area under each pole. So it will be actual length into the basically the pole arc, right, into the pole arc. Okay, this will be the area under each pole. So this can somewhere get asked, so might be important. Okay, so this was about the poles. Okay, armature winding in the poles. Okay, I think this much is cleared. So like before going into armature winding, few things I wanted to clear. Now let's discuss the conductors. Armature winding we have discussed, poles also we have discussed. Now let's discuss the conductor. Briefly I have shown you that there is a conductor. This is the conductor, right? So this is a single turn. It is a single turn, and in a single turn there are generally two conductors, right? Because the magnetic flux line will cut this first portion, the second portion, and this portion is actually known as the overhang, where there is no flux cut, right? There is the extra portion that is just there for the support, so this will not be utilized for cutting off the flux. That's why it is called as overhang. So conductor is the portion of the wire which is responsible for inducing the EMF. So where is the flux cutting? So in this portion the flux is cutting, in this portion the flux is cutting. That's why these two portions are known as the conductors. Okay, that's why this is the, like, let me name this A, B, C, D. So my AB will be one conductor. This whole thing A, B, C, D is a coil. It is a coil. Okay, one coil. And AB is one conductor, and CD is also one conductor. Okay, so these are the coils and conductors basically. So I hope you have understood this basic point. Okay, 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 this is one coil. Okay, so conductor is the active portion which is responsible for inducing the EMF. Okay, so from here I can develop a formula. So this is a single turn coil, right? One coil, one turn, right? What I can understand, for a single turn I have two conductors. For two turns, how many conductors I will have? 4. So number of conductors is equals to 2 times the number of turns. If the number of turns is 1, then I have 2 conductors. If the number of turns is 4, I will have 8 conductors. So this is a very important relationship that you must know. Okay, the number of conductors and the number of turns. Okay, so yeah, that was one thing about the conductors, right? So a conductor can be a single turn or a multi-turn conductor, right? It can be single turn and a multi-turn conductor. So how it can be a multi-turn? So it multi-turn, right? Basically this, let me delete this thing. This is not required actually. Let me delete this thing. So here, if I come back here, yeah, one more thing, that here, right, the conductor will carry current in this direction. Let me change the colors. Will carry current in this direction, and here the conductor will carry current in the bottom direction. Okay, these are the directions of the current. Okay, these are the directions of the current. So yeah, that's basically so here the current will be incoming, sorry, it will go, yeah, into the screen, and this will come out of the screen. So for the same coil, the directions of the current will be equal and opposite. This also I have mentioned in the initial lecture, right? Also mentioned in the initial lecture. So now let's discuss about the single turn and multi turn coil. So if it's a single turn coil, simply it will be a single turn only. If it's a multi turn coil, then this will have multiple conductors, right? This is 1, 2, 3, then this is 1, 2, 3, 4, right, on the left hand side, and then on the right hand side it is 1, 2, 3, 4. So basically it that's what a multi-turn coil is. Like for a single coil I have multiple turns. So if you see that this portion, this is known as the coil side also. Coil side 1 and coil side 2. So the direction of the current in the coil, each coil side, right, will be same. Okay, so I will write here, somewhere I will write, where shall I write? So I will write here only. So direction of current in each coil side will remain same. Okay, so why? If you see, this is the current direction, then it comes down from here, it comes down here, goes here, and then again here, right? So if you see the, if you will observe, right, you will observe this same thing, that it will come down here, it will come here, again it will come up here, again it will come down here, come up here, again it will come down here. Okay, so this is the coil side 1, right? First coil side, coil side. So each coil always will have two coil sides, right? Coil side 1, and this is the coil side 2, coil side 2. Okay, yeah, so that is the case over here. I hope you have understood about multi-turn. So multi-turn coil is, in a single coil there will be multiple turns. So this very basic formula will always remain, that the number of conductors will be 2 times the number of turns. So if you observe that here I have a single turn coil, I have 2 conductors. Here I have multi-turn coil. What is the number of turns? 1 turn, 2 turn, 3 turn, 4 turn. So how many conductors I should have? 8. 1, 2, 3, 4, 5, 6, 7, 8. So I have 8 conductors, right? So this basic thing I hope is clear to all of you guys, right? I hope you have understood this basic thing. And these are the definitions of coil and conductors. I hope you have understood, right? Yeah. So the terminals of each coil are connected to their individual commutators, okay, for rectification. So yeah, the two sides of the coil are wrapped together with insulating tape, because of course this is carrying current in one direction and the other side of the coil will carry current in other direction, right? So there must be insulation, else there will be short circuit. Okay, we don't want that. So there has to be proper insulation. Okay, so this number of turns can also be written as the this number of conductors can also be written as number of coil sides. Here how many coil sides I have? 8. Overall 8 coil sides. Here how many coil sides I have? 2. Here I have 8 coil sides, right? 4 on the left hand side, 4 on the right hand side. So this is known as the number of conductors, or here I have written Z is known as the number of conductors, or we can write as number of coil sides. And T is known as the total number of turns or the number of coils. How many coils I have? So single turn, single coil. Okay. So okay, we cannot write here number of coils actually, because it is a single coil only, right? Single coil has multiple turns. So yeah, it is number of turns only. This will be number of turns only. Okay. T will be number of turns only. Okay. So yeah, I hope basic understanding you have got. So one coil can have 2 into n number of conductors, because n is the number of turns. Okay, one coil will be if one coil each coil has 2 coil sides placed in different slots. So one coil has 2 into n conductors. Yes, one coil has 2 into n conductors, where n is the number of turns. Yes, one coil has 2. Yeah, it is correct. Okay, yeah, n is the number of turns. N basically is the number of turns. It is correct. So yeah, one coil will have 2 sides. One coil side will have n conductors. So if one coil has 2n number of conductors, right? One single coil side will have how many conductors? So this coil side has how many conductors? 1. This coil side has how many conductors? 1. So here how many coil sides I have? 4. How many conductors I have? 4. So remember this, that one coil side will be equals to the number of conductors. I mean whatever the conductors are there. So n conductors. Basically n is the number of turns, right? N conductors. Each coil sides will have n conductors. Okay, so one turn already we have discussed. One single turn will have 2 conductors. A single turn will have 2 conductors. Here I have multiple turns. it will have more conductors. One turn will have two conductors. Okay. Yeah, I think these are the relation that we are following, and that's it basically. One coil is 2n conductors. One coil. Now one coil can have n number of turns. N number of turns. So this is known as n turns. So if one coil has n turns, all these relations will be followed basically. Okay, and this is another diagram for multi-turn coil and a single turn coil. Okay, just diagram is not that important. Just like whatever I have shown it here, that is important. Okay, I've already told you what is overhang. Overhang is this portion, right? This portion is the overhang, which is the inactive part of the coil that connects the two active conductors at the back of the armature, but it's not responsible for the energy conversion. So basically that is known as the overhang. It just provides a electrical path. That's it. Not responsible for any flux cutting, something, right? Again, now another term is there, that is the coil span. So just like also known as the coil pitch, just like pole pitch, coil span or coil pitch tells us the distance between the slots where the two sides of the coil will be placed. So this is the armature, right? If I show you, okay, how do I copy? So or let me copy the actual diagram of the armature, that will be much better. So this is the armature, right? So let's say that the coil is placed here. Okay, the top side of the conductor coil is placed here, and the other side maybe from connecting from the back is placed somewhere here, right? There is the other side. So I current will be outgoing, I current will be incoming. So this distance, right, between the two conductors of the same coil is known as the coil span. So this is known as the coil span. So it is often expressed in the slots. So how many slot gap is there, right? After let's say 10 slots or something, we can say how many slots of gap is there after that the other conductor is placed. Okay, so there are two types of coil span. One is the full pitch coil, another one is the short pitch. In case of full pitch, right, the coil span will be equals to pole pitch. Both sides of the conductor lie under the same magnetic pole. Let's say if I have this, right, 4-pole machine. Okay, where did it go? So this is the 4-pole machine, right? So one side of the coil will be placed here, other side of the coil will be placed here. Okay, so let me copy the diagram. If it's full pitch, right, if it's full pitched, then not the coil, sorry, conductor. So let me reduce this here. Let me take it here. Let me explain it here. So what do I mean is that one of the conductor of the coil is placed here and the other conductor will be placed here. So what is the, like, either you can define it by the number of slots. So let's say how many slots are there. So gap 1, 2, 3, 4, 5. So you can say that the coil pitch here in this example, the coil pitch will be 5 slots. Okay, now if you want to define in terms of electrically, so if it's a full pitch coil, then the coil span or coil pitch, right, coil pitch will be 180 degrees electrical if it's full pitched. If it is full pitched coil. Okay, so basically why? Because again this is like if it's full pitch, that means that I will place them directly under the same poles, right? So what is the pole pitch here? 180 degrees electrical. So it will always be 180 degrees electrical. Coil span always will be 180 degrees electrical if it is full pitch. If it is short pitch, then it will not be placed exactly under the poles. Basically this is the case of full pitched. If it is short pitched, if it is short pitch, right, basically then the conductor will be placed somewhere here, right, not exactly under, right. So then the coil span will be something less than 180 electrical. Okay, in this case the coil span will be less than 180-degree electrical if it is short pitched. Okay, so this was about the full pitch and the short pitch thing, right. So the distance, right, when coil span is less than pole pitch, then it is called as the short pitch. Reasons for using short pitch: sometimes we want to reduce harmonics in the generated EMF. It will save us copper, because if I use full pitch, right, so the other portion, right, the distance is larger, so I will need more copper wires. So savings in copper, maybe we want to use, that's why we want to use short pitch, and it improves commutation. How, we will understand when we will discuss about commutation. So why we want to discuss, why we want to keep full pitch? Advantage is maximum EMF is induced in both conductors because they experience peak flux variations in opposite direction. So at same point of time, this will, let's say this will experience plus Bm flux, this will experience minus Bm. So the difference is huge, I mean difference is more, so the current also will be peak higher, right. So the flux waveform also will be more sinusoidal. That is what we mean, the flux waveform will be more and more sinusoidal. Okay, so in short pitch coils, the chording angle is the angular displacement in electrical degrees by which the coil span is less than the full pitch. So basically pole pitch minus the coil pitch or coil span, both of them are in electrical degrees, is equals to the chording angle alpha, right. So this factor cos delta by 2, it tells us how much the EMF will reduce. So if I make it short pitch, right, so the flux density will not be plus Bm minus Bm anymore. So if it is not plus Bm minus Bm anymore, the induced EMF also will not be totally sinusoidal. So the factor by which the EMF will reduce, right, this is defined by the chording angle, that is the cos of the alpha by 2. Not that important. Important for AC guys. For gate guys, you can ignore this. No need to remember this formula. For gate guys, it is totally, you can ignore this. So this will be alpha by 2, not epsilon. Gate guys can totally ignore this, but for AC guys, they can somewhat know about this. Okay. Okay, so yeah, that is about it. Basically these are the few theoretical points that I had to explain. In the next lecture we will start with armature winding. Okay, that is a very important portion, very important for gate. This lecture just I wanted to give a brief about the construction features of a machine. So I hope you have enjoyed this lecture. If you did, make sure to hit the like button, and I will see you in the next lecture. Until then, happy learning.